A planet 124 light-years away from us is quietly exhaling a molecule that on Earth is produced only by life, breathing it into an atmosphere thick enough for us to read through the light of its star. And no one expected that a world so distant and alien could leave a signal clear enough that scientists must open a debate unprecedented in the history of astronomy. Stay, because I am about to walk you through exactly what James Webb has just confirmed about K218b, what the scientists still do not dare conclude, and a discovery even larger than the controversy that almost no one is talking about. And please hit subscribe right now, because this channel analyzes real space discoveries without any hype, and you do not want to miss what else is emerging from the universe beyond the solar system. Let us go back to where this story truly begins. Because the history of K218b is stranger than most people imagine. In 2015, a small group of astronomers sifting through data from the Kepler Space Telescope in an extended mission called K2 were assigned one of the most tedious jobs imaginable. Night after night, they scanned thousands of stars looking for the tiniest dimmings when a planet crossed in front of its host star. Most of those dimmings led nowhere. Then in that stream of flickering data, Foreman Mackey and colleagues spotted something orbiting a little-noticed star designated K218, a faint dip that shifted with exact regularity every 32 days, and that dip was soon confirmed by Monte and colleagues as a real planet. They named it K218b. For years afterward, it remained just one entry among thousands on the list of newly confirmed exoplanets, even though it was so distant and faint that astronomers could only guess what it might actually look like up close. Its host star turned out to be an M3V red dwarf with only half the mass of our Sun, located about 124 light-years away in the constellation Leo. The planet has a mass of roughly 8.6 times Earth's, and a radius about 2.6 times Earth's. What stood out was that it lies in what astronomers call the habitable zone, the range of distances around a star where temperatures could allow liquid water to exist. But it must be said at once that lying in the habitable zone does not mean it is habitable. It only means it is neither too hot nor too cold relative to the liquid water threshold. Nothing more is guaranteed about water, atmosphere, or actual conditions. At the time of its discovery, K218b was merely one item on a list of thousands of candidates awaiting confirmation. There was no press conference, no headlines, no one outside the specialist community paid attention, and the class of planet to which K218b belongs, a sub-Neptune larger than Earth and smaller than Neptune, is a type that has no counterpart in our own solar system. It is worth pausing a moment to understand how little we actually knew about exoplanets before James Webb began operating. For most of the history of exoplanet science, earlier generation telescopes could measure only two things about these distant worlds: their sizes, inferred from the tiny dimming of starlight each time the planet crossed in front, and their masses, inferred from the extremely subtle radial velocity wobbles of the star as the planet gently tugged it back and forth. The dimming when a planet transits its host is so small it is almost unbelievable. Kepler could detect them only by watching thousands of stars at once and patiently hunting the tiniest dips in the data stream. It is like standing many miles away, looking at a street lamp, and noticing the exact moment a moth flies across the bulb. For hot giant gas planets extremely close to their stars, the so-called hot Jupiters, the transit spectrum was large enough that older instruments could read atmospheric composition to some degree. But for smaller planets, from Earth size up to Neptune size like K218b, the atmosphere was essentially a complete black box. That meant thousands of exoplanets had been confirmed in the first 2 decades of the field, yet the very thing that could tell us whether they had water, whether they had life, how much carbon was in the air, was something we simply lacked the tools to read. Then in 2019, a research team tried to do the nearly impossible. In September 2019, after years of quiet analysis, 2 completely independent research groups on 2 different continents published a result that shook the astronomy community. Both claimed to have found traces of water vapor in the atmosphere of K218b using the same data source from the Hubble Space Telescope. The first group, led by Angelo Siris at University College London, published their results in the journal Nature Astronomy. The second group, led by Björn Bennecke at the University of Montreal, used exactly the same Hubble WFC3 dataset, but with independently built analysis software. Both teams found the same absorption feature at a wavelength of about 1.4 microns, a band where the water molecule leaves its characteristic chemical fingerprint. Both teams interpreted that feature the same way. K218b has water vapor in its atmosphere. The European Space Agency and the Hubble team issued an official press release. This was the first time in the history of the field that water vapor had ever been reported in the atmosphere of a planet lying in the habitable zone outside the solar system. In the days that followed, global media covered the story intensively, as if humanity had just found the first livable planet with water. Siris was quoted repeatedly by major newspapers. He carefully said that K218b is not Earth 2.0, but it brings us closer to the most fundamental question humanity has ever asked, whether Earth is truly unique. The feeling at that moment is hard to describe. After decades of groping, humanity had for the first time touched empirical evidence of liquid water on a mid-sized planet beyond the solar system. Yet even as the announcement was made, some scientists carefully warned that the picture might not be entirely as it appeared. Hubble, for all its legendary status, was never designed for this kind of work. It could read only a narrow slice of wavelengths, and at 1.4 microns it is not only water that leaves a fingerprint, the signal both teams saw could be water vapor, but it could also be methane. Hubble's data simply were not sharp enough to distinguish the two possibilities. The problem lay in the instrument itself. Hubble had only a small window for observing exoplanet atmospheres. The WFC-3 instrument that both CRS and Beneke relied on could read only the wavelength range from about 1.1 to 1.7 microns, and at 1.4 microns, both water vapor and methane leave very similar absorption features. In 2022, Bazard and colleagues published an analysis proposing a troubling possibility. Hubble might indeed have read one of those two molecules, but with such a narrow wavelength range, the instrument simply could not tell which was water and which was methane. The answer would have to wait for a sharper tool. This was not the fault of CRS or of Beneke. Both had done exactly what could be done with the tools they had. The problem was only that the tools were insufficient to settle the question. What the researchers needed was not a better Hubble. They needed a telescope that could read a wavelength range many times wider with far higher sensitivity, and that is precisely what the James Webb Space Telescope was designed to do. Webb was launched on Christmas morning in 2021, after roughly a quarter century of construction at an estimated cost of about $10 billion. Its primary mirror, more than 6 meters across and gold-coated, folded like origami to fit inside the launch rocket, and then slowly unfurled in deep space a million miles from Earth at a special location called the Lagrange point L2. Its sunshield, the size of a tennis court, cools the instruments to temperatures lower than any freezer ever built on Earth. Hundreds of deployment steps had to work perfectly, in exact sequence, with no possibility of repair. All of them succeeded. The principle Webb uses is the same one Hubble tried, but on an entirely different scale. When K218b crosses in front of its star, a tiny fraction of the starlight passes through the planet's atmosphere before continuing toward us. Every molecule in that atmosphere absorbs light at its own characteristic wavelengths, leaving a distinctive chemical fingerprint. If we catch that starlight and split it with enough precision, the missing wavelengths in the spectrum tell us exactly which molecules the light has passed through. It is worth pausing to think about what that really means. The light Webb is collecting from K218b today left the star in Leo around the year 1902, before your great-grandparents were born. It traveled 124 light-years of empty space, then in the final few minutes of its journey skimmed the sky of an alien world before continuing more than another century until it fell into a telescope built by human hands. The difference between Webb and Hubble is not only mirror size. Webb reads a wavelength range roughly 10 times wider than Hubble could see. The scientific community spent years preparing for the first Webb observations of K218b. If you are the kind of person who wants space science explained clearly rather than buried under jargon, hit like right now. In September 2023, a research team led by astronomer Niku Madhusudan at the Institute of Astronomy of the University of Cambridge published the first results from Webb on K218b, and the fog that had covered this planet for years finally began to lift. Using data from NIRISS and NIRSPEC spanning the wavelength range from 0.9 to 5.2 microns, the team extracted the transit light spectrum with unprecedented precision. The results were stunning. Methane appeared clearly in the data at roughly 5 sigma confidence, meaning the probability that the signal is random is less than 1 in a million. Carbon dioxide also appeared at about 3 sigma. This was the first time in the history of the field that carbon-bearing molecules had been confirmed in the atmosphere of an exoplanet lying in the habitable zone. But there was a surprise in the data, and it completely changed how we must look back at the Hubble discovery 4 years earlier. Across the wavelength range Webb could read, there was no water. The absorption feature at 1.4 microns that CRS and Beneke had interpreted as the signature of the water molecule turned out to be methane. This is a moment worth pausing over. In 2019, CRS and Beneke did exactly what could be done with the tools they had, and they interpreted the data in the most reasonable way according to the knowledge of the time. In 2022, Bazard was right to be skeptical. And in 2023, Webb delivered the clear answer. No one in this story did anything wrong. Each step simply brought us a little closer to the truth. Yet if what Webb found was surprising, what Webb did not find may be even more important. Across the entire atmosphere of K218b, there is almost no ammonia. This absence may sound like a minor technical detail, but it is a very large clue. Chemistry tells us that if K218b were simply a pure gas ball all the way down to its core, ammonia should be clearly present in the upper atmosphere. Ammonia forms very naturally in hydrogen-rich atmospheres at those temperatures. That it has almost completely vanished means something beneath the atmosphere is quietly removing it. Something is absorbing it out of the air as soon as it forms. And one of the leading explanations for this is as elegant as it is strange. We will return to that later. What is admirable in this story is not that Webb was right and Hubble was wrong. What is admirable is that science corrected itself honestly and methodically. When exoplanets are studied with more precise tools, what once seemed settled can be rewritten. Not because the earlier science was wrong, but because science advanced. But deep inside the Webb data from 2023, the Madhusudan team noted yet another signal, much weaker than methane and carbon dioxide, not yet strong enough to announce as a detection, but intriguing enough to be worth pursuing. It was a hint of a molecule called dimethyl sulfide, abbreviated DMS. And this is where the story turns into an entirely different dimension. On Earth, DMS is not produced by volcanoes, not produced by lightning, not produced by rocks, not produced by any ordinary ocean chemistry process that we know. It is produced almost entirely by life, by microscopic phytoplankton drifting in our oceans. The mild sea smell you catch when standing on a beach on a windy afternoon is in large part DMS. It is the breath of an ocean full of living organisms. The Madhusudan team decided to return to K218b with Webb once more, but this time using an entirely different instrument. MIRI reads the wavelength range from 6 to 12 microns, an infrared window completely separate from the range that NIRIS and NIRSPEC had used. If DMS truly existed in the atmosphere of K218b, MIRI would see it at a completely different set of wavelengths. This would be a form of independent confirmation of the most natural kind possible in science. The same planet, the same molecule, but two entirely different fingerprints in two different spectral regions. The results were published in April 2025 in the journal The Astrophysical Journal Letters. The MIRI spectrum matched DMS, or its close relative dimethyl disulfide, abbreviated DMDS, at the 3 sigma level. The estimated concentration was not a tiny amount. It was more than 10 parts per million by volume, more than 10 million times higher than the concentration of DMS in Earth's atmosphere. At the Cambridge press conference, Madhusudan called this the strongest sign yet of the possible presence of life beyond the solar system. But he immediately stressed in the same sentence that this was not a certain detection. It is worth pausing a moment to understand the meaning of this moment. This was the first time in the history of science that a potential biosignature had been detected at a concentration high enough to be measurable in the atmosphere of a planet lying in the habitable zone. But if you want to understand why Madhusudan was so careful when announcing the result, you need to understand what 3 sigma actually means. 3 sigma means there is roughly a 0.3% chance that the signal is the result of random noise. That sounds almost certain, right? 99.7% confidence. But science has been burned many times before by signals at exactly this level. In physics and astronomy, the gold standard for declaring a real detection is 5 sigma. The probability of a fluke at that level is about 1 in 3.5 million. 3 sigma results die frequently. They are the universe's favorite way of teasing scientists. They appear clear enough to generate excitement, yet weak enough to vanish when upon closer inspection. The Cambridge team knew this well, and said so straight from the beginning. But the DMS story has a second layer of complexity beneath the statistical question. Even if the DMS signal were confirmed at 5 sigma, a larger question would still need answering. Is DMS truly produced only by life? Or are there unknown abiotic processes that could also produce it at similar concentrations? These are 2 completely different questions, and both must be answered before anyone can speak the word life. The Cambridge team knew very well that they did not yet have the answer to either of those 2 questions. And from the day of the announcement, they themselves called on independent research groups around the world to re-examine their results. Even before Webb published any results on K218b, Madhusudan had proposed a class of planet that had never before had a name in the astronomical classification tables. He called it a Hycean world, a portmanteau of hydrogen and ocean. The idea was put forward in 2021 and sounded almost like science fiction when first read. A planet with a global liquid water ocean covering its entire surface, above which sits a thick hydrogen atmosphere, unlike Earth with its thin atmosphere of nitrogen and oxygen, unlike Neptune with no real liquid surface. Hycean is an entirely new type, and K218b fits the Hycean prediction almost uncomfortably well. But this is where the missing ammonia detail from the Webb data of 2023 becomes especially important. One elegant and strange explanation for the absence of ammonia is an ocean. A vast planet-wide ocean of liquid water lying just beneath the hydrogen-rich sky, quietly absorbing ammonia out of the air above it. A gigantic mass of water silently cleaning the sky from below. Additional evidence also came from the same Webb data of 2023. The ratio of carbon dioxide to methane in the atmosphere is roughly 1:1, a number that matches with astonishing precision what Hycean models predict for a liquid ocean beneath a hydrogen layer. But there was another finding from the 2025 data that was almost completely overshadowed by the DMS controversy. A team at NASA's Jet Propulsion Laboratory, led by Renyu Hu, pointed Webb at K218b for 4 additional transits with a precision never before achieved. When the team modeled what kind of planet could produce exactly this atmosphere, the answer made even them pause. K218b could be a water world, not a dry rock, not a mini gas giant. A planet in which water could make up a significant fraction of its entire mass, possibly up to double-digit percentages. To grasp what this number means requires a comparison. On Earth, water accounts for only about 0.02% of the mass. Every ocean, every river, every ice sheet you have ever seen in your life is merely a thin film on a rock ball. K218b could be water on a scale for which we have no words in our language. Yet the very moment the Hycean evidence seemed strongest was when other research groups began proposing alternative explanations. Shortall and colleagues suggested that no liquid ocean might be needed at all. The absence of ammonia could be explained by a molten magma ocean beneath a thick hydrogen layer. Yang and Hu proposed another explanation. The roughly 1:1 carbon dioxide to methane ratio could also be produced by a water vapor-rich mini-Neptune with a deep atmosphere and no liquid water surface whatsoever. Wogan and colleagues used photochemical models to test 3 different scenarios. What is unfolding is a rare situation in science. The same dataset is matched nearly equally well by 3 completely different physical models. K218b could be the first confirmed Hycean world in history, or it could simply be an ordinary sub-Neptune that we are trying to imagine as more than reality allows. This is where the K218b story begins to show us how science actually operates when confronted with an extraordinary claim. Immediately after the DMS results were published, independent research groups around the world began downloading the MIRI data and reanalyzing it from scratch. Jake Taylor at the University of Oxford showed that the data might contain no significant spectral features at all. Luke Wellbanks and colleagues used a library of 650 different molecules and discovered that ethane, a simple hydrocarbon unrelated to life, could look almost identical to DMS at the resolution Webb currently achieves. In October, Stevenson and colleagues at Johns Hopkins University published a peer-reviewed result in the Astronomical Journal with a blunt conclusion: in 87.5% of valid data reduction pathways, the DMS signal does not appear. Then came the turn no one saw coming. In 2024, scientists analyzing data from the European Space Agency's Rosetta mission found DMS on a comet, a frozen ice body with no life. DMS has also been detected drifting in interstellar clouds. Laboratory experiments have shown that DMS can form through pure chemistry with no biology required. The molecule everyone had called the smoking gun of life turns out to have very solid abiotic alibis. The same Renyu Hu team at NASA JPL also published the conclusion that DMS could be produced by abiotic photochemistry right in the atmosphere of K218b. The same group that had just confirmed a water world also weakened the DMS signal. Madhusudan replied to CNN with humility that we never reached that level of evidence. This is moderate evidence, not a strong detection. By 2026, only 6.6% of astrobiologists agreed that K218b might have life. If you find this story as strange and fascinating as I did while researching it, leave a comment and let me know. It really helps me know which space stories are worth covering next. Now try to picture it for a moment, because the details are almost impossible to imagine without someone carefully describing them. If the Hycean hypothesis is correct and this remains unconfirmed, what would it be like to stand on K218b? Overhead hangs a red dwarf star, K218, much closer than the Sun is to Earth, yet far dimmer. The light arriving from it is not the yellow-white light you are used to, but a warm, muted orange-red. The sky above is not blue like Earth's sky because the atmosphere is mostly hydrogen rather than nitrogen. It might take on a pale pink or orange hue depending on the haze of the day, but in reality there is no standing in the Earth sense. There are no continents, no islands, no dry land. Only water from horizon to horizon in every direction you look. You would float rather than stand. If somehow you could stand firm on an imaginary surface, gravity would pull you down with a force about 20 to 30% stronger than Earth's. Atmospheric pressure pressing on you would be many times higher than Earth's. Right beneath your feet would lie a global ocean. The water could be hundreds or thousands of kilometers deep before reaching the higher pressure layers below, far deeper than any human submarine could survive. Into darkness and pressures beyond any experience our species has ever known. A day on K218b, if you wanted to count it in familiar terms, would last longer than an entire Earth month because this planet takes more than a month to complete one orbit around its star. But the day-night rhythm could be stranger still. K218b is likely tidally locked to its host star, meaning one face of the planet always points toward the star in eternal day, while the other always faces away in eternal night. And the terminator zone, the narrow strip between day and night where the orange-red light of K218 forever skims the horizon, could be the most interesting place on the entire planet. This is what Hycean models predict. But it is equally possible that K218b has no surface at all and is simply a hazy mini-Neptune with no liquid water anywhere. We truly do not yet know. The idea of an ocean beyond Earth is not new in science. Right inside our own solar system, scientists have long suspected hidden oceans beneath the icy surface layers of certain moons. Europa, Jupiter's fourth largest moon, is the most famous candidate. Beneath an ice crust estimated at 15 to 25 kilometers thick, a global liquid water ocean is believed to be kept warm not by sunlight, but by continuous tidal friction generated by Jupiter's enormous gravitational field. Enceladus, a much smaller moon of Saturn, has even more direct evidence. From its south pole, water geysers shoot straight into space with enough force that the Cassini spacecraft could fly through them and sample the material. That is probably the clearest evidence we have of a subsurface ocean beyond Earth. Titan, Saturn's largest moon, may contain a water ammonia ocean beneath its outer ice shell, and on its surface sit actual lakes of liquid methane, the only extraterrestrial lakes in the solar system that we have directly observed. Ganymede, Jupiter's largest moon, may have an ocean sandwiched between multiple ice layers of different densities like a gigantic water and ice sandwich. But there is one important common feature among all these oceans. All of them are completely sealed beneath a hard ice crust tens of kilometers thick. They do not contact the atmosphere. They do not contact starlight. Any life that might exist there would have to evolve in eternal darkness, relying on chemical reactions at the ocean floor rather than any light energy source. If K218b truly is a Hycean world as Madhusudhan proposes, its ocean would be completely different from anything we know in the solar system. No ice shell above, only a thick hydrogen atmosphere. The ocean would contact the atmosphere directly, just as Earth's oceans contact the air. And the orange-red light of K218, though far dimmer than sunlight, could still reach the water surface and penetrate to a certain depth. If any life existed in the ocean of K218b, it could photosynthesize. It could use the light of its host star the way terrestrial plants use sunlight. This is something no subsurface ocean in the solar system can allow. Not Europa, not Enceladus, not Titan, not Ganymede. If K218b is truly confirmed as a Hycean world, it would not only open a new class of planet in the astronomers' classification tables, it would open an entirely new kind of potentially habitable world, different from Earth. Different even from the hidden ocean moons we already know in our own cosmic backyard. It is worth pausing a moment to understand why scientists care so much about K218b, even while everything remains uncertain. Because even if the Hycean hypothesis is correct, an ocean is only a paradise if it is the right kind of ocean. The same models that allow a warm, habitable ocean also allow far darker outcomes. If the cloud layers in the atmosphere do not reflect enough starlight back into space, the surface could become too hot. At those temperatures, water would exist as a supercritical fluid, a crushing, extremely hot state that is neither gas nor liquid and hostile to any life chemistry we know. And above all, there is the star itself. Red dwarfs are notorious for their violent temperaments. They unleash flares many times stronger than the sun and batter their planets with continuous radiation. K218b orbits its star much closer than Earth orbits the sun. Whether life could survive under such a sky for billions of years is one of the largest open questions in modern astronomy. But this is where the K218b story truly shines. Before Webb, the question of whether there is life beyond Earth was a philosophical question. Webb plus K218b has for the first time turned it into an empirical question that can be argued with real data. No result is a failure. If DMS is confirmed as biological, K218b will be the first evidence of life beyond Earth. If DMS is abiotic photochemistry, we learn something new about hydrogen atmosphere chemistry. If K218b is merely a hazy mini-Neptune, we learn that indirect signs can mislead. This is perhaps the most admirable aspect of the entire story. It is not a discovery. It is a moment in which humanity's oldest question finally begins to have a method for being answered. Right now, there is no way to confirm anything about K218b directly. 124 light-years sounds abstract until you convert it into a concrete number. That is roughly 1.17 times 10 to the power of 15 kilometers. Voyager 1, the fastest spacecraft humanity has ever launched away from Earth, is drifting through interstellar space at about 17 kilometers per second. At that speed, reaching K218b would take roughly 2.2 million years. No mission is currently planned. No technology now existing can shorten that timescale to anything feasible within the lifetime of a civilization. Webb is the only tool we have, and Webb has its own limits. But here is where a rather surprising ray of hope appears. Luque and colleagues calculated that distinguishing the DMS signal from a flat noise floor would require about 25 more Miri transits. Yet the Cambridge team itself has a different estimate. They say that only 16 to 24 additional hours of telescope time could push the result to 5 sigma and end the question forever. Whatever the correct number, the main message is the same. The final answer is only a few days or weeks of Webb time away, not many generations. But each transit occurs only about every 33 days. That means a definitive answer on DMS at K218b could still take several more years, if Webb is still operating by then. At present, every few months when K218b again crosses in front of its star, Webb collects another dataset. And the overall picture continues to grow stranger than we expected. The path to the finish line is clearly visible. It is only a question of when we will reach it. This is perhaps the detail worth thinking about longest in the entire story. K218b is not special because of its location in the Milky Way. It is special because it belongs to the most common type of planet our galaxy knows how to make. Sub-Neptunes, planets sized from roughly 1.7 to 3.5 times Earth, account for about 30% of all confirmed exoplanets. And the strangest part is that our solar system contains no sub-Neptunes at all. Nothing in our cosmic backyard for comparison. That means the most common type of planet in the universe is also the type we know the least about. In NASA's exoplanet catalog, thousands of sub-Neptunes have been confirmed, yet most have never had their atmospheres studied. If K218b truly is a Hycean world, that means thousands of other planets out there could be the same. The number of potentially habitable places in the galaxy would not merely increase, it would explode. From the handful of Earth twins we once hoped for into billions of ocean worlds hiding right before our eyes. Future missions will expand this list very quickly. The European Space Agency's Ariel, scheduled for launch in 2029, will read the atmospheric spectra of thousands of exoplanets. The extremely large telescope with its Andes instrument could detect oxygen molecules in the atmospheres of Earth-sized planets. And NASA's Habitable Worlds Observatory is designed specifically to search for biosignatures. K218b is the rehearsal. It is where humanity is learning molecule by molecule, mistake by mistake, how to read an alien sky correctly. So that when the day finally comes when a signal appears and survives every test, we will know beyond all debate exactly what we are looking at. So what does all of this add up to? K218b could be the first planet with life that humanity has ever detected, or it could simply be an ordinary sub-Neptune that we are trying to imagine as more than reality allows. But what is truly special is not the final answer, it is the process. In a mere 3 years, a claim was made, tested by dozens of independent research groups, cross-checked against data from comets and interstellar clouds, and corrected by the scientists themselves in public light. The K218b story is not less interesting once the headlines fade. It is more interesting because now we know exactly what we are looking at. If you want to see space stories told this way, based on real research rather than exaggerated headlines, subscribe to this channel and turn on notifications. Because Webb is still observing K218b, and the next round of data may add yet another strange piece to this puzzle.